Hello students, this is Dr. Nita Raj, your chemistry mentor, welcoming you for another session in polymers. Today we shall see about the classification of polymers, right? So the polymers are classified in number of ways depending upon different criteria. So let us see one by one. First classification is classification based on source or origin, and the next one is classification based on synthesis. Next one is classification based on structure. The next one is classification based on molecular forces. Okay, so let us see one by one. The first one is a classification based on a source or origin. Okay, see, under this classification we are having three categories. The first one is a natural polymers. Okay, so what are natural polymers? So from the name itself it's possible to understand, right? The polymers which occur in nature are called natural polymers. Okay, so these are the substances of a natural origin. Actually these are found in nature mainly in plants and animals. Okay, the well-known natural polymers are proteins. Okay, and we are having some examples too. So the polymers like polymers, proteins, polysaccharides, rubber, silk, wool, starch, cellulose, enzymes, natural rubber, hemoglobin, all these comes under natural polymers. Okay. Actually, these proteins are the polymers of amino acids. These polysaccharides are the polymers of monosaccharides, and this rubber is a polymer of isoprene units. Okay, so likewise, it goes on, right? So these are the examples of natural polymers, right? So the next category is semi-synthetic polymers. What are semi-synthetic polymers? Actually, these are the polymers derived from naturally occurring polymers by chemical modifications. By doing certain chemical modifications on some naturally occurring polymers, it's possible to arrive at the semi-synthetic polymers. Okay. So here I have given some examples: cellulose acetate, gun cotton in vulcanized rubber, etc. Okay. The last one is the synthetic polymers. So what are synthetic polymers? See, these are the polymers which are synthesized in the laboratory. Okay. So these are man-made polymers actually. So the polymers synthesized in laboratory are called the synthetic polymers. A list of important synthetic polymers are given below. Okay. They are polyethylene, polystyrene, PVC mean polyvinyl chloride, bakelite mean phenol formaldehyde resin, then nylon 66, Teflon, then synthetic rubber. All these comes under synthetic polymers. Okay. Actually, these synthetic polymers are man-made polymers and they find a variety of applications in our day-to-day life. Okay, most of the synthetic polymers are long-chain organic molecules containing thousands of monomer units. Okay, whereas in the case of semi-synthetic polymers, this vulcanized rubber is a semi-synthetic polymer. It has much improved properties as compared to natural rubber. Okay, compared to natural rubber, this vulcanized rubber is having much improved properties and is used in making tires, etc. Okay. Actually, this gun cotton is cellulose nitrate and it is used in making explosives. Okay. Next type of classification is based on synthesis. See, under this category, we are having two types. The first one is addition polymerization or chain growth polymerization. So, what do you mean by addition polymerization or chain growth polymerization? See, when a large number of monomer molecules are added up together to form the polymer chain, the process is called as addition polymerization. So, here a large number of monomer molecules added up, okay, together to form a polymer chain. Okay, so this is called as addition polymerization. Actually, the monomers involved in this process are unsaturated compounds, commonly the derivatives of ethene. Okay, actually this type of polymerization does not involve the elimination of small molecules like water or ammonia or alcohol, etc. Okay, let's see an example for this category, that is a formation of a polymer or polyethene from ethene. Okay, CH2 double bond CH2. Okay, so this is ethene. Okay, now this n number of ethene molecules they combine to give polyethene or polyethylene. Okay, CH2. See what happens here. This goes this side. So CH2. Again, we'll have a bond here, and here also always the polymer will be represented by giving n at the suffix. So this is polyethene. Okay, this is polyethene or polyethylene. Okay, so this is ethene, right? So this is an example for addition polymerization. Actually, in this case, in the addition polymerization, it doesn't involve the elimination of any molecules like water, ammonia, alcohol, etc. Therefore, the repeating unit is the same as the monomer unit. Okay. Actually, the polymers formed by addition polymerization are called as addition polymers. Okay. So this is an example. Next, we shall see the next category, that is condensation polymerization or step growth polymerization. Actually, it is the process of combination of monomers with the elimination of a simple molecules such as water or alcohol or HCl or carbon dioxide or ammonia. See, in this case, in addition polymerization, there is no elimination of all these substances, whereas in this case, that is condensation polymerization or the step growth polymerization, there will be elimination of either water or alcohol or HCl or carbon dioxide or ammonia. Some elimination will be there in the case of condensation polymerization, and here also the monomers will be combining, okay, but there will be simple elimination. Let me give an example for this category, that is methylene diamine, that is H2, NH2, CH2, 6 times, then NH2. Okay, hexamethylene diamine, right? This is hexamethylene, 6 methylene groups. So hexamethylene diamine. This is hexamethylene diamine. This combines with adipic acid. Okay, adipic acid CH2 4 times. Okay, this is adipic. Here we'll have one COOH. Here also we'll have one COOH. Okay, and obviously you should write n number of hexamethylene diamine and n number of adipic acid combines. Okay, here there will be elimination of water molecule. Okay, there will be elimination of water molecule, and we'll get, see, like this it goes, hydrogen, one hydrogen from this amino group and OH from this group. Okay, this will be getting eliminated. Okay, likewise, here also this hydrogen from one hydrogen from this one and another adipic acid molecule from the other side, there will be elimination of water molecule. So likewise, there will be elimination of water molecule, and finally we'll get nylon 6,6. Okay, NH, CH2 6 times. Now NH, C double bond O, CH2 4 times, C double bond O, then close the bracket, N times. Here also. Okay. See here, what happens here, there will be elimination of water molecule. Here also this OH will go. Here one hydrogen it will go. Okay. So we'll be getting finally nylon 6,6. Okay. So nylon 6,6. Actually, this type of condensation polymerization occurs between monomers containing two or more functional groups. Okay. Here we are having amino group as a functional group, whereas here we are having COOH as the functional group. So, as I told you earlier, this type of polymerization occurs only between monomers containing two or more functional groups. Okay. Each step in this polymerization involves a loss of small molecules like either water or ammonia or alcohol, etc. So therefore, the repeating unit in this condensation polymerization is not the same as that of the monomer. Okay, so the final product will not be the same as that of the monomers what we are using, since there is elimination of some molecules like water, alcohol, or HCl, or then some other things. Okay, and examples under this condensation polymerization are bakelite, nylon 6,6. Okay, then alkyl resins, etc. Understood? Next, we shall see the classification based on structure. So, under the classification based on structure, the first one is the linear polymers. Okay. So, these are the polymers in which the monomers are joined together to form a long straight chain. Okay. So, the monomers will be joined together to form a long straight chain. Okay. So, let me give the schematic representation. This is how the linear polymers would be. Okay. So the monomers will be attached in a straight chain, okay, joined together to form a long straight chain. Okay, so these are called as linear polymers. And coming to the properties, they have a well packed structure. Actually, in the case of the linear polymers, The polymeric chains usually stack one over the other and form a well-packed structure. Okay, so due to the close packing structure of these polymers, these linear polymers they have high densities, they have high tensile strength, and also high melting point. Can you understand? So the next type of polymer is the branched polymers. Actually, these polymers they consist of side chains attached to the main chain. So this is the main chain. Okay, these are the main chains, and these are the side chains. Actually, due to the presence of this branching, these branched polymers they have a irregular structure. Okay, they have a irregularly packed structure. Okay, due to the presence of branching, the branched chain polymers are unable to pack themselves in a compact manner. So that's the reason why they are having a irregularly packed structure. Okay. And because of this irregularly packed structure, they are having low density. Okay. They have a low densities. They have low tensile strength as well as low melting point. Okay. So low density polythene is an important example of this category, right? So let us see the third one, that is a cross-linked polymer. What do you mean by cross-linked polymer? Actually, these are the polymers which consist of polymeric chains linked together through side chains to form a three-dimensional network structure. So in the case of branched structure, we are having a linear chain and we'll be having some side chains. Okay. But here what happens is the polymeric chains will be the linear polymeric chains, different chains will be linked together by side chains to form a three-dimensional network. Okay, it forms a three-dimensional network structure. So the polymeric chains will be linked together through the side chains to form a three-dimensional network structure. So that is called as cross-linked structure. Okay, actually, such type of polymers also are also referred to as network polymers. Okay, they are also called as network polymers due to the presence of cross links. Okay, and obviously because of this three-dimensional network structure, they are very hard, rigid, and brittle too. Okay, and some examples of this cross-linked polymers are bakelites. Bakelite is nothing but it's a polymer formed between phenol and formaldehyde. It's also called as a phenol formaldehyde resin, and then melamine formaldehyde resin is also an example of this category. Then urea formaldehyde resin is also an example for this type of category. Can you understand? And the last type of classification is classification based on molecular forces. Okay. So under this category, the first one is the elastomers. Actually, in these polymers, the polymeric chains are linked by the weakest intermolecular forces. Okay. So in these polymers, the polymeric chains are linked by means of weakest intermolecular forces. Okay. So see, let me give some examples. These elastomers, rubber bands. Rubber band is an example for this elastomer. Coming to the properties, actually due to the presence of this weakest intermolecular forces, these elastomers can be stretched. So such type of polymers consist of randomly coiled polymer chains. So when a force is applied on the randomly coiled chains, these randomly coiled chains they get opened up and the polymers get stretched. Okay. See, in order to help the polymer to retract to its original position on the release of applied force, a few crosslinks are generally introduced between the polymer chains. Can you understand? So these are the characteristic features of the elastomers, right? So next we shall see the next type, that is fibers. Okay. So what are fibers? In these polymers, the polymeric chains are linked by the strong intermolecular forces like hydrogen bonds or dipole-dipole interactions. Okay. So due to the presence of a strong intermolecular forces, they have a close packed structure and this imparts a crystalline nature. Okay. This is the reason why it's having a crystalline nature because of the close packed structure. Okay. And because of this crystalline nature, they have a sharp melting points. Okay. So they are interrelated. All the properties are interrelated. Strong intermolecular forces also lead to the close packing polymeric chains in them, and this imparts the crystalline nature to them. And this is why the fibers are having sharp melting points. Okay. And example for this category is nylon 66. Okay. So nylon 66 is a polyamide and is an important example of this type of polymer. The next example of this category is polyester. That is, an example is terylene, dacron, etc. Okay, and also these important fibers consist of strong dipole-dipole interactions. And the next type is thermoplastics. Actually, these are the polymers in which the intermolecular forces of attractions are intermediary to those of elastomers and fibers. So, in the case of elastomers, we have the weakest intermolecular forces. In the case of fibers, we have hydrogen bonding and dipole-dipole interaction as the intermolecular force. Whereas in the case of thermoplastics, we have for intermolecular force of attraction in which lies between elastomers and fibers. And these are the examples of thermoplasts. Okay. Actually, these thermoplasts are linear polymers with no cross-linking between the polymeric chains. Okay. So they are the linear polymers. Okay. And they have no cross links, and also at room temperature they are hard but they can be softened on heating. Actually, due to the presence of moderate intermolecular forces of attraction, these thermoplastics they get softened on heating. Okay, but at room temperature they are quite hard, but on heating they become soft and viscous. However, on cooling them they again get hardened. Okay, so as heating does not cause any cross linking, they can be easily molded by heating. Okay, so the process of heating, molding and cooling can be repeated as many times as desired without affecting the mechanical properties of the polymers. So without changing the mechanical properties of the polymers, it is possible to heat them, then again mold them, then cool them. Okay, so there will be no change in their mechanical properties. So for some common examples of this type is polythene, then a polypropylene, polyvinyl chloride, polystyrene, Teflon, etc. So all these comes under this thermoplastics. Okay. So these thermoplastics they are a reversible, meaning on heating it gets softened and then at room temperature it gets hardened and again on heating it can be converted to a soft material. Can you understand? Okay. So the next type is thermosets. So what are thermosetting polymers? These are the polymers which on heating change irreversibly into hard, rigid and infusible materials. Okay. So these polymers on heating they change and but finally it becomes hard, rigid and they are infusible materials and it is not possible to change them again. Okay. Those four type of polymers are called as thermosetting polymers. Okay. Actually, these type of thermosetting polymers are usually prepared by heating relatively low molecular mass semi-fluid polymers in a mold. Okay, so on heating, they become infusible and form an insoluble hard mass. So why it becomes hard? The hardening on heating is due to the formation of extensive cross-linking between the different polymeric chains. Okay, so extensive cross-links are formed between the different polymeric chains. This is the reason why they are becoming so hard. So looking into the properties, they have a three-dimensional network polymers. So since the three-dimensional network structure is rigid and does not soften on heating, the thermosetting polymers cannot be reprocessed. Okay. Some of the examples of this category are phenol formaldehyde resin, melamine formaldehyde resin, urea formaldehyde resin, etc. Okay. So next we shall see about the plasticizers. So what are plasticizers? So the plasticizers are the organic compounds added to the thermoplastics to increase the workability. Okay, in order to increase the workability, the plasticizers or the organic compounds which are added to the thermoplastics. Okay, so actually these plasticizers help to soften the thermoplastics at lower temperature and thus make them a molding easier. Okay, some examples. See, this is a schematic representation. This is the image of a thermoplast without a plasticizer. So on adding plasticizer, it becomes a little flexible. Okay, and some of the example of this category are a dialkyl phthalate and cressyl phosphates. Okay. Actually, we all know PVC. It's not PVC, polyvinyl chloride, and it is a tough thermoplast. Actually, it is used. Actually, it is made workable by the addition of a dibutyl phthalate, which makes it soft and easily moldable. Understood, students? Well, fine, students. I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session. Until then, it's Dr. Anita Raj, your chemistry mentor, signing off from me. Thanks for watching.